Hi everyone, today we are going to discuss how to find out the Fourier series of f of x in the interval minus pi comma pi. So this is Dr. Ravindranath Reddy working as assistant professor in MLR Institute of Technology, Hyderabad. So now in this video, we are going to discuss what is an even function, what is an odd function, how to find out the Fourier series of f of x in the interval minus pi comma pi. Now we will see what the definition of even and odd functions. Okay, now I have taken a function f of x and now I want to say that function f of x is an even function. So in order to identify that is even or odd, so replace that f of x with a minus f of x. So if that f of minus x is equal to, once again if you get the same function f of x, then this function we can call it as an even function. Suppose if you take one example here, so f of x is equal to x squared. Now I want to check whether this function is an even function or odd function. Now replace that x with minus x here. So you will get minus x whole square. So minus x whole square, once again we can get that value is equal to x square. This x square is equal to f of x. Now even though if you replace x with minus x in the function, once again we are getting the same function as f of x. Then this function we can say that f of x is equal to x square is an even function. Suppose even though if you replace x with minus x in the function, if you get that value is equal to minus f of x, then this function we can call it as an odd function here. So let us take one example here. So f of x is equal to x. Now in this function I want to replace that x with minus x here. So you will get this value is equal to minus x, and this can be written as minus. In place of x I want to replace that value with f of x. So f of minus x is equal to, here we got that value is equal to minus f of x. So this function f of x is equal to x is an odd function here. Okay, suppose even though if you replace that x value with minus x, so sometimes you will not get that f of x value or minus f of x, neither f of x nor minus f of x. So whenever we don't get any of these two options, then that function is said to be neither even nor odd. For example, if you take f of x is equal to x squared minus x. Now in this function replace x with minus x here. So you will get this value is equal to minus x whole square minus of minus x. Now this is equal to x square minus into minus plus x. So this is not equal to f of x, and this is also not equal to minus f of x here. So whenever we replace x with minus x in the given function, if that value is not equal to f of x or not equal to minus f of x, then this function we can call it as neither even nor odd. So these are the three important definitions we have to know whenever we are going to find out the Fourier series in the interval minus pi comma pi. Based on this only we are going to find out the Fourier series for the given function. We will take the Fourier series of f of x in the interval minus pi comma pi. So in this I am taking the function as neither even nor odd. So whenever we are having f of x is neither even nor odd in the interval minus pi comma pi, we will see how to find out the Fourier series expansion here. So the Fourier series of f of x in the interval minus pi comma pi is given by, so f of x is equal to a naught by 2 plus summation n is equal to 1 to infinity a n cos nx plus b n sin nx, and similarly this a naught value is given by 1 by pi into integral minus pi to pi f of x dx. Now by using this definite integral we are going to find out the value of a naught, and next a n value. So a n is given by 1 by pi integral minus pi to pi f of x into cos nx dx. By using this definite integral we are going to get the value of a n, and Bn is equal to 1 by pi integral minus pi to pi. Here we are taking the interval minus pi to pi, so we have to consider these values as the limits of that integration while you are finding the coefficients a0, an and bn. So these are the standard, and in this we can call it as a Euler's coefficient or Euler's formula. Now we will take one example for the function f of x in the interval minus pi comma pi, and then we will see how to find out the Fourier series expansion here. Now this is the function he has given. We have to obtain the Fourier series expansion for f of x is equal to x squared minus x in the interval minus pi less than x less than pi. This also we can take it as minus pi comma pi. So in this interval, for this function we have to find out the Fourier series expansion. So once after finding that Fourier series expansion, by taking the help of that Fourier series expansion, we have to prove this condition. Now we will see how to prove this. Now this is the function he has given, f of x is equal to x squared minus x. Now the Fourier series for this function is given by, this is the standard formula we are having to find out the Fourier series. F of x is equal to x squared minus x, which is given by a0 by 2 plus summation n is equal to 1 to infinity an cos nx plus bn sin nx. Now these are the coefficients we have to find out, a0, an and bn values here. Okay, once after finding these values, an value, bn value and a0 values, if you substitute that values in this equation 1, then we can get our required Fourier series in the interval minus pi comma pi for the function x squared minus x. Now one by one we will see how to find out the coefficient values, a0 value. First we will see how to find out a0 value here. So this is the standard formula we are having, 1 by pi integral minus pi to pi f of x dx. Now I want to replace that f of x here. F of x, he has given that f of x is equal to x squared minus x. Now find out this integral value. So now separately here in the function we are having two terms, so I want to apply the integration separately for each term here. So integral minus pi to pi, the first term is x squared minus, here we are having minus, so keep minus, and the integration for the second term, that is x. So integral minus pi to pi x dx. Already we have the standard formula, we know how to find out the integral of x squared. So the integral of x squared is given by x cubed by 3, and here once if you observe this second integration, so whenever we are discussing the integrations between minus pi to pi or minus a to a or minus infinity to infinity, we have to concentrate on the function and we have to check whether that function is even function or odd function here. So now here, this by default here we are having x, so you consider this as f of x. Now check whether this function is a even function and odd function. So x is an odd function here. So since this is a odd function, so whenever we are having an odd function inside the integral whose limits are minus pi to pi or whose limits are minus infinity to infinity or minus a to a, then directly we can take that integral value is equal to 0. So that's why here we have taken 0. Now once if you observe the first integral here, so here x square is an even function. So whenever we are having an even function inside the integral whose limits are minus pi to pi, then this integral can be written as 2 into integral 0 to pi x squared dx. So we have the standard formulas, we have seen these values in the lower classes, integral minus a to a f of x dx, and this value we can take, this value is equal to 0 when f of x is an odd function, f of x is odd, and this value can be written as 2 into integral 0 to a f of x dx. So this is possible when f of x is an even function. Now this is our standard formula. Based on that, so this a value, it may be pi or it may be 1, or you can take any values for a. So whenever we are having the integrals in limits are in this form, then we can use this formula here. So similarly, we have applied the same formula here. We got this integral 2 into integral 0 to pi x square dx. Now integral of x square, we can take that value is equal to x cube by 3. Now substitute the upper limit and lower limit here. So when we substitute the upper limit and lower limit, then we will get this value is equal to 1 by pi. And now take this constant outside, 2 by 3, and now substitute the upper limit pi. So you will get this value is equal to pi cube minus 0. Now this is equal to 2 by 3 pi and pi square, pi cube. So 1 pi gets cancelled here. Finally you will get this value 2 pi square by 3. So this is the value of a0 here. Now in the next we are going to see how to find out that an value here. So this is the standard formula we are having. An is equal to 1 by pi integral minus pi to pi f of x and f of x into cos nx. Now replace that f of x with its value. So that f of x value is x squared minus x, and write down this cos nx as it is here. Now remove these brackets by multiplying this cos nx here. So first term x square into cos nx, you will get cos x square cos nx minus x into cos nx. So x into cos nx. So inside the integral we will have two terms. So separately apply the integral for each term separately here. Now here also the integral limits are minus pi to pi. So whenever we are having these type of integrals, then concentrate on the function and identify whether the function is an even function or odd function here. Okay, x square, this is an even function. Just now we have seen this x square is an even function, and this cos is also an even function. So whenever we multiply two even functions, then this resultant product of these two functions is always even function. Okay, so in the first integral, we are having the function as even function. Now go for the second integral. So here x is odd function and this cos is even function. So cos is an even function, because if you replace cos of minus x, once again we will get the same function cos x. So that is equal to f of x. So cos is an even function. So whenever we multiply an odd function with an odd even function, then the resultant is always odd function. Now inside the integral we are having an odd function. Just now we have seen in the how to find in the while you are finding a0 value, we have seen whenever we are having an odd function inside the integral whose limits are minus pi to pi, then we can consider that integral value is equal to 0 directly. That is the advantage of that standard formula. Okay, so that's why we have taken. So here x squared into cos nx we have considered as an even function. So this as even function, and x into cos nx we have seen that as an odd function. So since here is an odd function, so this integral value can be written as 0. So I have neglected that second integral since it is 0. Now you concentrate on this first integral here. So it is an even function. So whenever we are having an even function inside the integral, that can be written as 2 into integral 0 to pi x squared cos nx dx. Now it's time to evaluate this integral x squared cos nx dx. So inside the integration we are having the product of two functions. One is x square, which is an algebraic function, and having another function cos nx, which is an trigonometric function. So inside the integral we are having a product of two functions. So we have to apply integral of uv, that is integration by parts. Okay, so yesterday in the previous we have seen how to identify the u and v by using the word highlight, and also we have seen the standard formula to find out that integral of uv formula. So integral of uv, we have this. So this can be written as u into v1 minus u dash, that is derivative of u into v2, plus u double dash into v3, until we have to repeat this until we get the derivative of u as a constant. Now here v1 is nothing but integral of v, and v2 is equal to integral of v1, and v3 is nothing but integral of its previous integral, that is v2 value. So v3 is equal to integral of v2. Okay, apply the same procedure here. So you will get, so the first one is u. So we have considered u is equal to x square. So we have kept that x square into integral of v is nothing but cos, integral of cos nx, that can be written as sin nx by n, minus a derivative of u, that is derivative of x squared, that is 2x, into v2 is nothing but integral of v1. So this is the value of v1. Now once again you find out that integral value here, integral of sine, we can take it as minus cos nx, and here we are having nx, so we have to apply the derivative and we have to take that derivative in the denominator. So already we are having n, so if you apply this once again integration, once again we will get another n in the denominator, so it can be written as n square, plus 2 into, once again this is v2. Now once again apply the integration here, you will get minus cos nx by n3. Okay, so this is the integral value by using this integral of uv formula. Now simplify this and substitute the upper limit and lower limit here. So the first upper limit is x square. So in place of x, substitute the upper limit a pi. So it becomes pi squared sin n pi by n. So minus into minus, so we can take it as plus 2 into x, that is 2 pi cos nx, x is replaced with pi, we will get cos n pi by n square, plus 2 into minus sin n pi by n cube, and substitute the lower limit, minus of lower limit is 0. So x squared, if you replace x with 0, 0 into anything equal to 0, the first term becomes 0. And here also if you replace x is equal to 0, 0 into anything equal to 0, the second term also becomes 0. And now the third term, you substitute x is equal to 0 here, it becomes sin 0. We know that sin 0 is a 0, 0 into anything equal to 0, 0 by anything equal to 0. So when we substitute the lower limit x is equal to 0, these three terms becomes 0, so we can neglect that. Now you concentrate the next one. Now here we have the standard formula sin n pi. Sin n pi is always equal to 0. So I have kept 0 into anything equal to 0. So the first term becomes 0. Plus here cos n pi. We have the formula cos n pi is equal to minus 1 whole to the power of n. This is the standard formula we are having. So 2 pi by n square, in place of cos n pi I have taken that minus 1 whole to the power of n. And here we are having sin n pi. We know that sin n pi is equal to 0. We have taken that value equal to 0. Now simplify this, we will get our required an value here. So an 2 into 2, 4. This pi and this pi gets cancelled. So in the denominator we will get only n square, and is next one multiplication with minus 1 whole to the power of n. So this is the way how we can find out that an value here. So we got an is equal to 4 by n square minus 1 whole to the power of n. Now we will go for the last quotient, that is bn. So bn is equal to, this is the standard formula to find out the bn value. Here also you follow the same procedure what we have followed to find out an value. So replace f of x by its function value, so that is x squared minus x. Then remove that brackets by multiplying with sin nx, and then apply the integration separately for each term. So this is the way, similar to the previous one. So now once again the integral limits are minus pi to pi. So whenever we are having these integral limits minus in this form, minus pi to pi, we have to concentrate on the function, whether it is an even function or odd function. So already we have seen x square is an even function and the sine is an odd function, because we will get sine of minus x is equal to minus sin x, which is of the form minus f of x. So that function we can call it as an odd function. So whenever we multiply one even function with an odd function, definitely this resultant function is always an odd function. Okay. So next go to the second integral. X is an odd function and the sine is also an odd function here. So whenever we multiply odd function with odd function, then this resultant is always an even function. Okay. So since in the second integral we are having an odd function and the integral limits are minus pi to pi, so integral value, so first integral value we can consider that value is equal to 0. The same thing we are going to discuss here. Now the first integral limits becomes 0, and since it is an odd even function, so this can be written as 2 into integral 0 to pi x sin x dx. Now evaluate this second integral, then we can get our required bn value here. So here also we are having x into sin nx, which is a product of two functions. So x is nothing but an algebraic function and sin is a trigonometric function. So you have to apply integral of uv formula. Apply the same formula what we have applied in the previous an. So same. So 2 by pi, you take the 2 x into integral of sine, you will get minus cos nx by n minus of minus, this is the uv formula we applied. Then substitute the upper limit and lower limit here. So sin n pi equal to 0, you substitute that value, and finally you will get this value is equal to 2 by n cos n pi. So already we have seen cos n pi, we can replace that value with minus 1 whole to the power of n. So 2 by n minus 1 whole to the power of n. So this is the value of bn. Now we got a naught value, bn value, an value. Now you substitute all these values in the equation 1. Okay. Now this is our, after substituting that a naught, an, bn here in equation 1, we got this value. Now simplifying this, finally we got x by pi square by 3 plus summation n is equal to 1 to infinity. Now here, now this is our required Fourier series for the function x square minus x in the interval minus pi comma pi. So whenever the given function is neither even nor odd in the interval minus pi comma pi, then we have to find out a naught, an and bn, all these three coefficients here. Okay. Now once if you observe our course problem here, after getting that Fourier series expansion, by using that Fourier series expansion, we have to reduce this condition here. Now we will see how to reduce this condition. Now this is our Fourier series expansion for the function x squared minus x. Now in this expansion, put x is equal to 0 here. So you substitute x is equal to 0 throughout this equation 2. So 0 squared minus 0, that is 0. Pi squared by 3, since it is a constant, so we can take that constant as it is, plus summation n is equal to 1 to infinity. So here if you substitute x is equal to 0, you will get cos 0, and we know that the cos 0 value is always equal to 1. So 1 into this one, you will get this value, plus here substitute x is equal to 0, you will get sin 0. Sin 0 is 0, so 0 into anything equal to 0. So this entire second term becomes 0. So we have neglected that second term and we got this resultant value. Now simplify this. You expand this one. You send this pi square by 3 to this side. You expand this. You will get these terms here and simplify this. Finally, you will get minus pi square by 12 is equal to the required condition here. So in the problem, there is a scope to prove the scope to derive the Fourier series expansion, and by using that Fourier series expansion, we have to reduce some conditions. It will be given in the question. Okay. So this is the way how we can find out that Fourier series expansion for the function in the interval minus pi comma pi. So finally, you will get this value here. Now in this video, we have seen how to find out the Fourier series whenever the function is f of x is neither even nor odd in the interval minus pi comma pi. In the next video, we are going to discuss how to find out the Fourier series for the function f of x when it is an even function and odd function. Both we are going to discuss in the next video in the interval minus pi comma pi. Thank you all.